So when we're talking vertex coloring or grouping, we use something called the chi of G. This is the chi of G, or the chromatic number of a graph. This is the minimum amount of colors or groups that a graph can be vertex colored. Now, we have several versions of this theorem called Brooks' theorem, but we use the strong version. So let D1 be greater than D2 or equal to D2, be greater than or equal to D3, be greater than or equal to D to infinity. Be the degrees of the vertices of a connected graph G listed in decreasing order. So that means D1 is the highest degree. If G1 is not an odd cycle, which has its own rules, or Kn, or complete graph, which also has its own rules, then the chromatic number of the graph is less than or equal to the highest degree. So the chromatic number of a graph is less than or equal to the highest degree in that graph. So that'll come in handy. So here is the rules for cycles. Here's a C3, here's a C4, here's a C5, here's a C6. Now this should remind you of my definition of bipartite when I was trying to show you what that means. If this vertex is red, B or C cannot be red, so I need to make them a different color. Now, C cannot be red or blue, so it's going to be green. So the chi of C3 is 3. The chi of C4 is going to be 2, because if you remember, C4 and all even graphs are even cycle graphs are bipartite. So if D is blue, then E can be green, F can be blue, and G can be green. So if we look at C5, this is an odd cycle, so it's going to be 3 colors. I'm going to do 2 colors until I absolutely have to add a 3rd color. So I'm going to go back and forth between green and blue until I absolutely have to add a 3rd color. I cannot make vertex L green or blue, so it has to be red. So the chi of C5 is 3. C6 is even, so every other one, it's going to be 2. The coloring number is 2. We'll make it yellow. I like this section, it gets colorful. So the chi of C6 is 2. So the rule here is that the chi of Cn is 2 when n is even. the chi of Cn is 3 when n is odd. Okay? Remember, odd cycles are not bipartite, even cycles are bipartite, which means it can be split up into two groups. Let's look at complete graphs. We know that a K3 is 3. We've already done it. I'm just going to go ahead and use numbers. 1, 2, 3. Let's look at a K4. The chi of K4 is, I got to use numbers. 1, none of the vertices connecting to vertex D can be 1, so E has to be vertex 2. Vertex F cannot be a 1 or a 2, so it needs to be a 3. Vertex G cannot be a 1, a 2, or a 3, so it needs to be a 4. In K5, if vertex H is 1, I cannot be 1, so it has to be 2. Vertex J cannot be 1 or 2, so it has to be 3. Vertex K cannot be 1, 2, or 3, so it has to be 4. Vertex L cannot be 1, 2, 3, 4, so it has to be 5, so the chi is 5. The chi of K6 is 6. This is because every vertex in a complete graph is connected to every other vertex. Therefore, each vertex has to be an individual color. So the chi of Kn is n. It doesn't matter how many n it is. Now, going on to problem set 6, you'll still have to find another pattern, the wheel graph. I'm going to let you do that one on your own. But you're going to follow the rules just like I did in these note videos. Now let's talk about Brooks' theorem. I'm gonna grab a graph that is not a complete graph or an odd cycle, and I'm gonna explain Brooks' theorem. So Brooks' theorem says that the coloring number can be no greater than the highest degree. Okay, so here the highest degree is 3. So the coloring number here can be no higher than 3. So if E is red, nothing connecting to it is red. Now, if we look at this really quick, we can see that we have an odd cycle on the outside, so I know that this is going to be 3. No matter what I do, this has to be 3. I'll make that blue, I'll make this red, I'll make that blue. I can't make this red. So let's go make these blue or red or blue. So I'm going to go ahead and make this part yellow. So now I'm going to go back to E, and E cannot be red. I mean, J cannot be red, but it can be yellow or blue. So I'm going to go ahead and make it yellow. F can't be blue or yellow, so I'm going to make it red. Vertex I cannot be blue or red, but it can be yellow. Vertex G can just not be yellow. So I'll make it blue. Okay. Now, if I continue with this choice, my vertex H cannot be yellow, blue, or red. Brooks' theorem says I cannot go higher than 3. So that means I've made a mistake. If I make this guy red, then H cannot be yellow and it cannot be red, but it can be blue. And that is where Brooks' theorem comes in. Hopefully that helps. Happy mathing. Happy coloring. Whoops, that is not what I want to